Okay, let's continue. This is going to be Physical Science 201, Chapter 1, Scientific Units and Their Conversions, Part 2. Alright, Part 2. Alright. We already had 30 minutes of discussion. In Part 1, we start with the Scientific Units Introduction. And then that base units got 7 of them, and we introduce the 2. Links and math, right? Mass. And now we get into temperature. The temperature, I think the time, probably the time already, the timing on the camera already cut off early. So let's start from temperature again. Okay, now temperature actually in science, including engineering, have 4 different scales. We are not going to touch the engineering scale. I think it's R. Temperature scale symbol is R. We're not going to get in there. But we get into the 3 we normally use and in science. The one in science is called a Kelvin. It's a capitalized K. It's a capitalized K, alright, capitalized K, and without circle of degree sign on the up left corner. Now that is very, very important. It's not because I'm picky. It is science. Science is picky. Alright. There's no leeway, no room for error. Alright. So it comes from the name of engineer or scientist, and his name is Kelvin. Alright. And this scale only uses science, and use that Kelvin scale temperature measured, and it will fit into almost all the scientific equations in different fields. Alright. And lots of them in chemistry and physics. You have to use Kelvin. Right? Now, on the other hand, there are 2 more symbol representing 2 more scale of temperature in science. They are the Fahrenheit and the Celsius. Now, the Fahrenheit is only used in US. Right? It's only US. Oh, sorry. Should be the capitalized S. Alright, only for US. Now we measure our body temperature. If you're healthy, not sick, your temperature should be under 98.6 Fahrenheit. Normally in the morning it's going to be 1 degree lower, like 97.9 or 97.6. That's normal. But in the afternoon it goes up not beyond 98.6 degrees. If you go to 100 or 99 or something, you have a little fever. Now, in this country, I just learned in the recent past, if you your temperature don't go beyond 104 Fahrenheit, which is 38 Celsius, you're not considered sick with fever. That is absurd. Or you got 1 degree temperature higher than normal 37 Celsius or 98, you are 100.4. You are sick. It's even sicker if you have some problem with your lungs. You have TB, normally in the afternoon you will have a very small fever, which is about 1 degree or so every day. When the time comes to 5 p.m., 6 p.m., your body temperature goes up a little bit. And that means you have something wrong with your lungs, alright? TB maybe. Alright, that is what I know, what I remembered. Alright, and then the Celsius. Celsius is used by every country in the world except the US. But we know a little bit about it. However, we don't want to change. I said why we don't want to change is stick to the English system because the past history, right? We already talked about it. And then after the Great Depression, US was out of the Great Depression, become a creditor instead of debtor, and then a lot of countries owes up some money for land lease because of World War II. And everybody changed to international system, metric system, and this country said, I'm not going to change because I'm rich, I got a lot of money, right? And you have listened to me, US dollar is going to be the one used in market, and everything, the trade is going to be based on US dollar. But now we've got a problem on the science, right? Science, we don't use Fahrenheit, and then we use Celsius, the rest of the world. If you go any other country, and you have to know that, and but in science you have to use Kelvin. All right, that's in the world, entire world. Right. Now the conversion conversion between all three temperature scale in science is not just a conversion factor with a certain numerical number as the fold, like a 1 yard equals 3 feet. So it's 1:3 ratio, and 3-fold, right? 3 times bigger the number of feet than the yard. It's not just like that. It's going to be involving equations. We're going to introduce the equation for temperature scale conversion in the very near future. Okay. Here, if you talk about a couple of those temperature, we should know, right? And then the example, we can say, okay, body temperature, right? Temperature should be 98.6 Fahrenheit. Now, by the way, Fahrenheit is a symbol with a capitalized F with a circle on the upper left corner representing the degree, all right? But then the same body temperature in Celsius is only 37 degrees Celsius. That's capitalized C, all right? It's not italic C, and it's a little bigger. All right, also has circles. All right, these two are equivalent. So you don't see exactly what is the same 1:3 or ratio. You have to use the equation to convert between Fahrenheit and Celsius. Kelvin, same thing. All right. Now that's the temperature. The third base unit, number 4. Right. Number 4, we talk about time. Time scale. Right. And it just happened in the past. Time scale was set exactly the same between two systems. Between metric and English, both use second as the base unit. Alright, second. So that's a second. And that is second. Small s, not big s. Second. And then, but we have to know, the time scale is not based on 10, 10, 10, or 16, or 12. It's based on 60. But 60 only within 1 hour. Right? 1 hour equals 60 minutes, and then 1 minute equals 60 seconds. So I have asked so many students in the past, how many seconds per hour? People don't think a little deeper and then jump on it. It says 360. Now I put on my notes, I said very clearly, it's not 360, right? 60 multiplied 60, that's 3,600. If you consider your 1 hour is only 360 seconds, then your hour went by so fast, right? 10 times fast. So you're going to die 10 times faster than anybody else. Is that right? Because your time is short. So it is not. Because why? Because every second has a defined time duration or time interval. We normally say, did that means 1 second. So how long the sound, the did that, right, going to be said, that's how long the 1 second will take, right, in terms of time, right? So that is one. So if you only count 360 did that, and everybody else counts 3,600 did that for 1 hour, is that true? Everybody's time is 10 times greater than yours? And you probably dead a long time ago, right? So nobody can live 200 years old, and then if you're already 20, you'll be dead, right? You should be dead before you're 10, because you're 10 years old, actually is equivalent to what? To people, that's 1 hour to you. And then to everybody's 100 years. Right? So that is different. That is different. All right, so then after time, the number 5, another scientific unit is called amount of substances. Now, amount of substances, it is a very, very important unit, and it's kind of a little difficult for some students to handle, because we are going to involve something with the matter. The matter, the substances is matter in the universe or on Earth or in nature, right? And we talk about chemical compounds. And that's which substances we talk about. We talk rocks, we talk water, we talk air, we talk different gases, we talk different liquid, alcohol, Everclear, 100% alcohol, right? We talk about vinegar, we talk about all these things, and the gas we can talk about carbon dioxide, carbon monoxide. All those are chemical substances. And their amount is not going to be easy to count, but use this units we call amount of substances to count the number of certain units for the amount of substance. What is that units? That certain units we call mole. Now I already mentioned in my class. Now the shorthand is MOL. That's the shorthand, not much shorter, right? But what is the definition for mole, right? And mole, first, if you want to check the mole, you go to dictionary. And dictionary says there's several items named as mole. The first one is a little animal. We already talked about it in the class last Friday or Thursday last week, right? A couple of days ago. And that little thing, I hate it. And then a lot of people hate it because they dig around tunnel under the front yard or backyard and then destroy your yard, right? And the dirt come out and then it says it's very ugly. I don't know. Some people go online, check the picture for me, say that's not ugly. It's a little small animal, but I've never seen one. Right? Second item for same spelling in English for mole is the mole on the skin. Right? I think I would say here, if you see my arm, right? If I go get close to the camera, and you'll see on my arm I have a bloody red mole, and I can actually more than that. One here, those are moles, right? And there's another one right here. But the most famous mole is on somebody's lip, right? Whose lip? Cindy Crawford, right? The model, right? The supermodel, right? So she has a mole on her lips. And it's a beauty mole, right? That's a beauty mole. Then another meaning of mole on dictionary is spy. SPY, and doing espionage job for a certain government or certain organization, and then for killing or invasion or something. That's called a mole. The last one, that's what we talk about mole, M-O-L-E, is a unit for a fixed number of entities, right? For different type of chemical or non-chemical substances. Basically, it was designed for counting the number of atoms or molecules or chemical substances. If you have 1 mole of chemical substances, say you have 1 mole of atom of oxygen, then you are talking about 6.022 multiplied 10 to the 23rd power of units of oxygen atoms. So this one just happened to be, there's no counterpart for the English system. In English system we don't deal with the science often. So this mole is only for metric system, but I guess you can use the English system. If they talk about anything in English and in Britain and you talk mole, they still understand, right? So mole is for metric system, for chemistry or physics or any substance with a certain amount. So defined as mole as, so on my notes I say very clear, 1 mole of anything, right, will contain 6.022 multiplied 10 to the 23rd, right, units of something. Now that is a simple definition. You say, okay, that's not too hard. I can't handle that. Well, let's try if you are able to handle that, right? But anything or something can be replaced by anything or something, correct? So let's say if you have 1 mole of ping pong ball, well, how many ping pong ball individually we count is going to be what? Yeah, of course, it's going to be 6.022 times 10 to the 23rd ping pong balls and packed up in a big container. That container is going to be bigger. I think it's bigger than the size of Earth or something. Bigger than the size of Moon at least, I think. All right. And but what happens if we change from ping pong ball, right, to table salt, right? How can we figure out the size of 1 mole of table salt, NaCl? NaCl is what? Sodium chloride, right? We're going to talk about chemistry, a little bit chemistry at the end of this course, right? 3 weeks getting to chemistry. And we also involve chemistry before that, so we involve energy, involve enthalpy, you know, the evaporation, condensation, all these, you know, we involve energy and then the thermochemistry part. But here, let's talk about chemistry. If we talk about NaCl, you know, those are not molecules, those are ionic compound formulas, right? And then they were cation and anion combined, give a ionic compound called sodium chloride, NaCl. Everybody should know that. If you never heard that, that's fine. We make you up, right? We make you up. NaCl, it is 1 sodium atom combined with 1 chlorine atom, and they form 1 NaCl, and it's tiny, so small, right? So tiny, small. And then if we talk about this many sodium chloride units, they're all packed up, only take up the space of roughly, probably less than 1 tablespoon. So if you have less than 1 tablespoon table salt come from the jar or come from the cartoon you bought from Walmart, if it's not table salt, if it's a rock salt, whatever, you have this many, you only have 1 mole. But if we turn a big volume item, say human body, right? If you talk about 1 mole of human body, 6.022 multiplied 10 to the 23rd of human body packed up. I believe somebody made a calculation. It's going to be big enough to take up the space for the entire solar system, from the sun stretch to the edge of the solar system to Pluto, including the orbit of the Pluto entirely in a three-dimensional sphere. For that space can only contain 1 mole of human body. That is how big it is. All right. Now let's think about this number. Why that will be so big? Because human body is, you know, pretty good. You know, 5 feet tall, average 5 feet tall, and a certain weight, right? And then you pack them up, right? And just like a sardine, like a fish, you put in the tank or put in the container and then stack up. And then you talk about how many human body are going to be lined up in that exercises. Let's say exercises. It's going to be 6.02 times 10 to the 40. So how many zero supposed to be behind the decimal point? If you change the scientific notation into regular number writing, everybody should know 23 means what? 10 times 10 times 10 times 10, multiply 10, multiply 10, multiply by 10, 23 times by itself, right? So you're going to involve 23 zero after decimal point. How many zero will be 1 million? 6 zero, right? And how many zero will be 1 billion? 9 zero. So 23 is twice the 9 zero, even 5 more zero, because 9 times 2 is 18, only 18 zero. It's still what? 100,000 times less than 1 mole, because 1 mole is 5 more zero, because 23 minus 18, that's 5 again. 5 means 10 times 10 times 10 times 10 times 10. That's 5 more zero, that's 100,000 billion. And the 600,000 billion. That is the number of units for anything to be considered as 1 mole. Alright, as 1 mole. Okay, so if you write down this number, so it's going to be something, it's going to be what? 6, right? 0, 0, 0, 0, 0, 0, 0, 0, 0. Total number of 0 after 6 is 23, 0. That's huge number, right? And why we have to use this big number? Because atoms or molecules or ions in substances, they are so tiny small. The average size of an atom, I did not put in this notes, but on the chemistry class notes, I put down here. I can put down here, and also in the links, I can use the example, put down here, say, okay, the links, we could have another example, very useful for chemistry, is going to be, maybe erase here, alright, erase here, and alright, another is what? It's a 1 angstrom. What is that symbol? It's a capitalized A, right? With a circle on its tip. It reads, it's called angstrom. Angstrom. Angstrom represents the size of links. How much? Is 10 to 1 times 10 to the what? Minus 10 meter. That's a small one. Instead of millimeter, instead of micrometer, instead of nanometer. Nanometer is what? Nano, if you heard nano, nano means 10 to minus 9. This one, the angstrom, is 10 times shorter than 1 nanometer. So in other words, if you have 1 meter, what is 1 meter? 1 meter, this is meter stick. I think this is meter stick. Oh, this is not. This is a yardstick. That's only 91 centimeters. That's a yardstick. All right. And the 1 meter is going to be this long, about this long, 1 meter. All right. And they chop up into what? Into for 1 angstrom, 10 times 1 billion, 10 billion portion, chopped into 10 billion portion. 10 billion portion is, billion is 10 to 9, right? So nano is 10 to minus 9. 10 billion, chopped up 10 billion small sections, and each one is exactly the length of 1 angstrom. Why we have to introduce strange unit and size? Because that is the average diameter out of space. Average diameter. It is average diameter of an atoms of an atom. So that's why we in chemistry we talk about it, because here we haven't talked about it. But that's another thing. So here is going to be 23. So that's so small. So this many particle of atoms or molecule they packed up, right? Only very small size, like a teaspoon of table salt. That would be 1 mole, right? That would be 1 mole. So that is the unit. We're going to introduce that, and then but this we're going to in the near future we're going to talk about moles in little details. What is half mole? Well, half mole. What is quarter mole? Well, tenth mole. What is 3 mole? Or 10 mole? You just have to deal with those number in the front, right? And then we find exactly same power to 10, and with different first term in scientific notation, and they represent half mole, 3 mole. 3 mole, you have to multiply 6 by 3, become 18. But when we talk about scientific notation, the time in the future, we're going to say, okay, we have to move decimal forward 1, and then increase that 23 to 24. Now we're getting there in the near future. Don't worry about it. I just let you know a little bit ahead of time, so you got a good exposure. And in the near future, when we really discuss that, and then we are able to handle that much better. All right. So if we want an example, right? One example for the mole, amount of mole. So we're going to use that small space. Let's find out. Get some space, right? Let's erase this. Let's erase it. So let's do some exercises we already talked about. If it's a half mole, we have that number. We don't have that number. 3.011 times 10 to the 3 units of anything will be considered as half mole of something. Am I right? So if you have, say, it's quarter mole of apple. Oh, that's big volume. It take up probably the size of a moon, right? I don't know exactly. You can calculate the average size of apple and then use the geometry, right, to find out, right, how big size of moon, and is that going to be exactly the multiple, and then with 6.022 or not? Or so quarter is divided by 6. 6 divided by 4, right, become quarter, right? Multiply 1/4, that's divided by 4. Same thing. 6 divided by 4. Don't use your calculator. In my class, I tried to get you hooked on phonics with your brain. All right, now those handheld calculators, in case they're out of battery, right? And then I have to sometimes use it because the time consumed in the lecture only 30 minutes. I don't want to spend time on doing those, but most time I can do something very close enough to estimate, right? So 1.5 will be 1/4. So 1.5 something, right? And times the 10 to the 23rd, that would be quarter moles, right? If I have 2 moles of markers, right? Of markers, and then 2 mole, 1 mole 6.02, 2 mole will be twice of this number. So 2 times 6.02 becomes 12.044, right? And then times 10 to the 23rd, and then by the definition of a scientific notation, this is scientific notation. Scientific notation has 2 terms. The first term has to be less than 10, larger than 1, right? Or equal 1. And the second term has the power to 10. Power to 10 is 23 to 10, right? And then we cannot afford to use the first term more than 10. So if you times 2, become 12, and 12, so 2 mole. So 2 mole, example, let's say, example here, right? 2 mole apple. So you have 2 times 6.022 multiply 10 to the 23rd. Then you have 12.044 multiply 10 to the 23rd. Right? This is not allowed because this first term number larger than 10 is not allowed by scientific notation. So we have to move the decimal to the left. Right, to the left, in order to reduce the first term by 10-fold. But that movement of decimal equivalent to multiply 10 to minus 1. Correct? The decimal to the left, 10 times smaller. 10 times smaller means 10 to minus 1. 10 to minus 1 is what? 0.1, 0.1, right? But we cannot do that because if we change that decimal result to something in the 10 power 10, then the value will be 10 times smaller. So we have to maintain the same value of the entire number. So here you multiply 10 to minus 1. Then here we will compensate to multiply 10 to 1. Now, this process is represented by moving the decimal to the left of 1 place. Then decrease the value by 10-fold, which is not allowed. So the compensation process is multiply 10 to the 1, increase 10 times on the power to 10 term. So this whole thing will become what? So this, after this process, this number, correct written of this number would be what? Would it be equal 1.2044 times 10 to what? Yes, 24. So 1.2044 multiplied 10 to 24, that's the total number of apple if we deal with what? We deal with 2 moles of apples. Alright? And I think almost time's up. And then we introduced 5 of them. Let me use the last minutes. Talk about, right? We are not going to detail the number 6 and number 7, which is the current, electric current, and the luminescence of the lights. But that's the physics part. We're going to skip that. We only introduce in my notes. You will see it in my notes. But then we get into the conversion factors and how to do the conversion job. All right, time is up. And then see you part 3. All right, see you at part 3.